Before we do that, let's think about the relationship between inference and sampling. So I said that if we can do inference, that is, we can find the distribution over a single value, then we can very easily sample it just using our 1D sampling methods. Now that doesn't work in the case where we want joint samples, that is, samples of all of our values together. But let's not worry about that for now. So that is to say that if you can do inference efficiently, then you can sample efficiently. But in cases where we have a high tree width probabilistic graphical model, inference will be hard. Therefore, that method of sampling is not an option. However, if you can sample, I contend that you can also do inference efficiently, because if I create a whole bunch of samples, those samples I can use as sort of representatives of my distribution. If I want to know how often is x equal to 1, I can just generate, let's say, 1,000,000 samples and ask, in what fraction of my samples is x equal to 1? And that's a very good estimate for the true probability that x equals 1 according to my probability distribution. So in that sense, kind of inference and sampling are two sides of the same coin. Now, it turns out that using the methods that I'm going to tell you about in just a minute, sampling is often, we can often sample pretty efficiently even in cases where we don't know how to do inference efficiently. So often we'll use sampling for that purpose. That is, we don't care about the samples themselves. We don't want to necessarily use them. What we want is inference. That is, we want to know the probability of something in our model. We're going to use these very powerful methods for sampling for approximate inference. That is, we're going to generate a bunch of samples, and then we're going to ask the samples for an estimate of the probability of whatever event we want. And to take the probability according to a bunch of samples, I just, again, take all my samples and ask, in which cases does that event hold? I can ask, for example, in what fraction of samples is x equal to 1? In what fraction of samples is x greater than 5? In what fraction of samples is both x equal to 2 and y is less than -1? Any kind of event. To get an estimate from my samples, I just take the subset of samples that match that event, and then whatever fraction of the total samples that is, that's my estimate of the probability. So I would say this is really the primary use of sampling in practice, is to use it for inference. We're going to use these very powerful methods for sampling that we're going to talk about next, and use them to do approximate inference. The first method we're going to talk about is Gibbs sampling. Gibbs sampling, again, is a method for producing samples from a multivariate probability distribution, like a Bayesian network or a Markov random field. So what's a little bit different about Gibbs sampling than, for example, the forward sampling method we just saw for Bayesian networks is Gibbs sampling is an example of a Markov chain Monte Carlo method, MCMC. Although when people use the term MCMC, they're usually talking about the Metropolis-Hastings algorithm that we're going to talk about right after this. But what is a little bit different about this method is that our sample we're going to produce in the next step is going to depend on the sample we produced in the previous step. And I'll talk about the implication of that in just a minute. But let's define the algorithm. So what are we going to do in Gibbs sampling? So first thing, again, we have our Bayesian network, and we're going to initialize our samples randomly, let's say using a run of forward sampling. Then what we're going to do at each iteration, we're going to pick a variable. Let's say we pick C. We're going to sample a new value of c that we'll call xc indexed by t plus 1, because let's say our previous sample was t plus 1 is going to be our next sample. We're going to sample xc according to this distribution, probability of xc given xt, that is our x from the last iteration, minus c. With this notation minus c, I just mean all the variables other than c. From what we have done with d-separation, it's not hard to show that conditioning on all the variables other than c is equivalent to conditioning on what's called the Markov blanket of c. That is, any parent of c, child of c, or variable where c shares a common child. So for c, that's actually everything in the network. A is a parent, E is a child, D is a child, and B shares a child with C. The Markov blanket of E would be just C, of D it would be B and C, of A it would be A and B, and so on. That's the Markov blanket. Let's write it down. This distribution here we call the full conditional distribution. That is the distribution of x of c when we've defined a value for everything else. So that's essentially the whole algorithm. At each step, we pick a variable. Normally the thing we do is we go through each variable one by one, and then we start over. We sample xc according to that full conditional distribution. We record the full x as a sample, and we go again. We sample on one of our other variables, record that as a sample, continue going until we have many, many samples. By the way, if we have observed values, then in our initial sampling step, we just make sure that we assign them exactly to what we observed them to be. So for example, we could use forward sampling, and then instead of actually sampling our reserved values, we just set it to the appropriate value. And it's okay that we could have some observed value from parents where that's extremely unlikely. That will just eventually get fixed as we do the Gibbs sampling. Now, and then as we do our iterations, we just skip observed values. We still include them in the condition, we just never resample them. So that's Gibbs sampling. We do this for many, many iterations. We get a whole bunch of samples. And again, the main reason we want to do this is not necessarily because we care about having samples from the distribution, generally because we want to do inference using those samples. That is, when we're done, we're going to ask, for example, for what fraction of samples is x equal to 1. Now, something that's pretty surprising is that this procedure, if you run it for long enough, will converge to the true distribution p of x. That is, our samples are going to be such that they're drawn from the initial the true distribution. That's not obvious. We're not going to do the proof here. The proof is in the textbook. I encourage you to take a look. It's a bit tricky, but it's interesting. Anyway, but this is a fact that's true. There are some edge cases. I'm going to talk about the edge cases in towards the end of this week's lectures. The other thing to consider, again, I'll talk about this in a little bit, is that there's a burn-in period. That is, our samples, notice that our samples are dependent on one another. So each sample is not uncorrelated with the previous sample. That is, our samples are correlated with one another. That is to say that there's this burn-in period where the first few samples, generally the first several thousand or even millions of samples we produce, are poor estimates of our distribution. Generally, we throw away the first few samples we produce, because they're dependent on that initial sample we got from using, for example, forward sampling. That's generally going to give us a very bad sample, and therefore all those samples that were correlated with that are going to be crummy samples. The second thing is that because our samples are correlated with one another, 1 million samples from Gibbs sampling are worth a lot less than 1 million totally uncorrelated samples. That is, you can't sort of assume that 1 million samples are perfectly, perfectly independent, all good samples. But again, the properties of that large sample we get for running Gibbs sampling for a long time are going to exactly equal the true distribution. I'm going to talk towards the end again about how we diagnose mixing, which is what we call the case when Gibbs sampling has converged and now we have enough samples that they're that any inference we draw from that set of samples are good for inference. That's what mixing is. I'm going to talk about how we diagnose mixing versus non-mixing in a little. Let's do an example. So for example, let's use the Ising model. So recall that an Ising model is one where we have random variables in a grid like this, and this is a Markov random field. So in the Ising model, we have potentials for every pair of variables that are neighbors in this grid. So for example, we have a potential over x4 and x5. So recall that an Ising model is extremely difficult to do inference in. So it's not too hard to see that this Ising model has enormous tree width. The tree width is going to equal whichever is the smallest of the number of rows and number of columns. So I said that one example of when the Ising model is useful is for image denoising. So if we have an image of, let's say, 256 by 256 pixels, we get an Ising model with 256 rows and columns respectively, and the tree width of that model is 256. And again, recall that in the running time of inference using any of the exact inference methods we know of, including variable elimination, is exponential in the tree width. So we would have to take running time roughly proportional to 2 to the power of 256, which is totally unreasonable. So we're going to show that it's actually quite easy to get samples, or at least to run Gibbs sampling in the Ising model. Notice also that we don't even have a normalization constant for this model. So if we just give ourselves a bunch of potentials, which is generally what we're going to do in practice, in order to come up with the normalization constant, in principle, we would have to sum over all of the possible assignments of these variables. So all the possible assignments, that would be 2 to the power of 256 times 256 in the case of a 256 by 256 image. 256 squared is the number of pixels, so the number of assignments we would have to sum over is 2 to the 256 squared. And that's, of course, even more unreasonable than running variable elimination. So we have two problems. One, high tree width. Two, we don't even know the normalization constant, which, again, as I've mentioned, is the problem that we usually face. Because even in the case where we did know the normalization constant, often we would also have some variables that we want to marginalize away that would give us some new normalization constant that we would also not be able to compute. Okay, but let's figure out how we can do Gibbs sampling in the Ising model. So to do Gibbs sampling, there's only one derivation step that we need to do before we can start running it, and that is to derive the full conditional expression. That is, I need to figure out what is the probability of xt equals its two values. Here we have two possible values, +1 and -1, for white pixel or black pixel, given xt minus 1, and here we're explicitly conditioning on our parameters, which correspond to all the different values of our different potentials. So now again, to do this expression, we need to figure out which values xt is deseparated from. And it's not too hard to see that the Markov blanket, that is the subset of variables, such that if we condition on those variables, our variable is deseparated from everything else. In a Markov random field, remember, it's even easier than a Bayesian network. It's just the variables that variable is directly connected to. So here we're trying to sample, in this case, x8, and we need to look at the values of x3, 7, 1, 3, and, 13 and 9. Okay, to do that, well, we just plug into our probability distribution. And actually, so to do that, let's just remember that the probability of x, in this case our whole x, is just going to equal 1 over z times product of, for every pair ij, psi ij of xi, comma, xj. That's our probability distribution. Based on this, it's not too hard to see why we only need to look at the neighbors. Okay, so let's write down our full condition. So here, I need to put the probability of xt and x minus t, so that's the probability of everything. So here I would just put probability of the whole x here, divided by, I need the probability of just x minus t. Well, that's the probability of xt equals 1 and x minus t plus probability of xt equals -1 and x minus t. Right, this thing is just the probability of x minus t. There are only two possible values for xt, +1 and -1, so we just have to sum over those two values. Now notice that if I were to write this all out explicitly, any potential that didn't involve xt itself would come outside of this sum here and would cancel on top and bottom. So that's why what I've written here is a product over just those variables s that are neighbors of t, which in this case would be, again, x3, 7, 9, and 13. And I've written the product here of xst of these two, xt equals 1 and xs. Notice that we've chosen +1 here because that's what we want the probability for. Of course, the probability that xt equals -1 is going to be 1 minus the probability we get here. On the bottom, I have exactly the same thing. So notice that this thing and this thing match. And this thing is exactly the same. I've just substituted in xt equals -1 here. Notice we need a normalization constant for the top and bottom. but that normalization constant, whoops, cancels. So that goes away. That's why I didn't write this. Now notice that I can calculate all of these very easily. This top term is just a product of 4 factors. Each of these bottom terms, oh, this one is the same, so we only have to calculate once. This one again is just a product of four factors. So we could compute this full conditional very easily. We could even do it by hand. You wouldn't want to do a lot by hand, but you could do it a couple of iterations by hand. So even for this Ising model, which is extremely hard to do exact inference in, we can do Gibbs sampling no problem. So to get our samples, again, through Gibbs sampling, we would just keep going through all of our variables, resampling each one according to this full conditional, and then once we felt like we had done it enough, we would use that big set of samples as samples from our distribution. So just to give an example of how this works, what I'm showing you here, this is this image denoising task, where here is our initial noisy image. And we're going to, and we want a denoised version of this image. By the way, something I should mention is that we can also handle univariate potentials. That is where we have a potential over just x10, for example. I just for the sake of simplicity, I didn't include this here, but we would just have to put this into this product here. So with s's all the neighbors, so we'd have to add in additionally one more potential, which is also the univariate potential over t. Again, doesn't make it much harder to compute. It just means we're taking the product over 5 things as opposed to 4. So if we run Gibbs sampling, turns out to work very well. Here is what we do. What we did is we did 15 sweeps of Gibbs sampling. That is, we resampled each pixel. That was one sweep of Gibbs sampling. Then we did that 15 times. And what we're showing here is the average for each pixel of with what frequency it was sampled to be white versus black. So these dark gray ones are almost always sampled to be black. The white ones are always almost sampled to be white. And you can see this is a pretty good denoised estimate of our initial image.